Good morning, everyone. I am MD Shahriar Kobir, and today I will be presenting our work on SIR-DR, an autonomous ground robot for detecting bird droppings on PV panels using efficient data. This project focuses on making solar power generation more reliable by addressing a surprisingly small but critical problem, which is bird droppings. Over the next few minutes, I will walk you through our motivation, methods, results, and future vision for this system. Here is the roadmap for my presentation. Solar energy has become one of the most important renewable sources worldwide. PV panels are widely adopted, but their performance is slightly sensitive to soiling, especially bird droppings. These droppings can cut power output by nearly 24% and even cause hotspot that permanently damage cells. So cleaning them manually is costly and inefficient. During our research, we had the opportunity to interview engineer DM Majibur Rahman, the managing director of SCBL, who owns the largest solar park on Monpura Island in Bangladesh. He shared his experience saying the droppings of bird and bees fall on PV panels regularly. They are sticky and hard to clean without water and significantly reduce overall output. This shows how real and frequent the issue is in large-scale solar parks. So our project aims to address this issue and aligns with Sustainable Development Goals SDG 7 on clean energy, SDG 11 on sustainable cities, and SDG 13 on climate action. By ensuring clean panels, we are not just boosting efficiency, we are directly contributing to environmental sustainability. Many researchers have explored UAV or drone-based monitoring models like YOLO version 7, YOLO version 8, and CA YOLO version 5 have been applied successfully. But UAVs face challenges like wind, weather, and high computational demands. For example, strong winds can easily push a drone off its planned flight path, while a ground robot remains stable on the panel row. Drones also have limited battery life, often less than 30 minutes per flight, which makes continuous monitoring of large solar farms difficult. In contrast, ground robots can carry larger batteries and operate for hours without interruption. And finally, drones require trained pilots and regularly permissions to fly, while ground robots can be deployed without each restrictions. On the other hand, EfficientDate offers an excellent balance between accuracy and resource efficiency, yet few have explored its use in ground robots, which are inherently more stable, cost-effective, and practical for solar farms. So this is where our study bridges the gap. Now, basic idea of our project. The concept is simple but powerful. Imagine a robot is moving on the rows of solar panels. It stops at each panel, captures a high resolution photo, and sends it to the cloud. There, our deep learning model, EfficientDate, analyzes the images for droppings. If the bird droppings detected, the system can immediately trigger the cleaning process. This workflow reduces manpower, ensures timely cleaning, and most importantly, guarantee the solar panel operate at their maximum efficiency. For example, in a large solar farm, where thousands of panels across many rows, manual inspection could take several workers a day to complete. With our system, the ground robot can move on automatically and detect droppings within minutes. This way, maintenance teams are only sent to panels that actually need cleaning. In fact, sometimes an entire row might not require any cleaning at all, and our system ensures that no time, water, or manpower is wasted on unnecessary work. The construction and design of the robot. Our hardware is designed to be both affordable and scalable. The first component is a Raspberry Pi, which acts as the brain of the system. It manages everything like from the robot's movement to sensory inputs and communication with the server. A 5 megapixel Pi camera is mounted at the front to capture high-resolution photos of the solar panels. To ensure smooth navigation, we use ultrasonic sensors that measure distance and prevent the robot from drifting off its path. A metal detector circuit is placed to detect the exact edge of each panel, so the robot knows precisely when to stop and capture an photo without missing any panel. For mobility, the robot is equipped with a tank wheel system, which provides strong grip and stability on the panel surface. The chassis of the robot is 3D printed, which makes it lightweight, cost effective, and customizable. It also protects the electronic circuit board from dust and water, and in rainy days it can also service. Together, these efforts make a reliable and budget-friendly platform for PV panel inspection. Here you can see both the block diagram and the actual assembled robot. CNN-based bird droppings detection model. The brain behind detection in our system is a model called efficient rate. Let me explain why it's special. Most AI models need to look at objects at different sizes, sometimes very small, sometimes very large. For example, a bird dropping could be just a teeny spot or a big patch. Efficient handles this using something called BIFPN, which basically means it combines information from an image at different levels of detail. Imagine zooming in and out of the same photo. BIFPN takes the sharp detail from close-up views and the overall context from the wider views, then fuses them together to make smarter decisions. At its core, EfficientNet is powered by EfficientNet B0, which is a very compact and efficient backbone network. Then think of EfficientNet as a strong but lightweight feature extractor that quickly learns what's important in an image without wasting memory or speed. For training, we built a custom dataset of 1008 level images. Some panels were completely clean, while others had droppings of different sizes and colors. We then fine-tuned EfficientNet specifically for this two-class problem, clean versus dust. Training was done in TensorFlow using a GPU, so the system could learn efficiently. Now the performance analysis of the model. Let's look at how the model performed. We achieved 94% accuracy, 93% precision, and 94% recall. The intersection over union score averaged 0.81, which means our bounding boxes align very closely with actual droppings. These results show that the system reliably detects bar droppings of varying size and color, as you can see in the example on this slide. However, small or overlapping droppings remain a challenge, reminding us that more diverse data will further required to strengthen its performance. One of the strongest points of our work is affordability. The entire system, including Raspberry Pi camera, motors, sensors, and chassis, everything costs just $119. Compared to industrial inspection systems or drones, this is low. And we used 3D printed parts, which helped us cut costs further while allowing easy customization. This also makes our solution feasible not only for large solar farms but also for small community or rooftop systems. Environmental and social impact. Our system has good impact environmentally and socially. Environmentally, clean panels mean higher efficiency, reduced reliance on fossil fuels, and lower emissions of carbon. This strengthens climate resilience and supports the SDG goals. Socially, reliable solar power means fewer blackouts, fewer load sheddings, better access to the electricity in rural areas, and improved quality of life. Whether it's lighting for homes, powering hospitals, or enabling education more effectively. For example, in off-grid villages of coastal Bangladesh, even in a short blackout during the night can interrupt classes in digital schools or halt refrigeration of medicines in rural clinics. By keeping solar output stable, our system directly supports these essential services and ensure our improved social life. And financially, rooftop solar users can reduce their bills and even earn through net metering system. In short, this system empowers both people and the planet. Future work. We see big chances to make this system even better. First, we will add more data from different conditions like sunlight, bird droppings, and overlapping spots, so the robot can detect more accurately. Next, we will make it work smoothly on edge devices, so it can run in real time without always needing the cloud. We also plan to connect the detection with cleaning, so it can automatically detect, clean, and repeat the process. And finally, we want to use it on large solar farms, so it can make the system almost self-sustaining. These steps will help turn solar panel care into a simple, fully automatic process. Our system has some limitations. The dataset was relatively small, making teeny or overlapping droppings harder to detect. Then the efficient D0 also requires significant memory sometimes, which challenges to implement it in low power edge devices, and real-time streaming still needs improvement. Despite this, our conclusion and contribution is clear. We achieved high accuracy with 94% performance metrics in detection bar droppings. The overall robot detection system low cost at around $119, which makes it accessible and affordable. And the system supported sustainability, boosting solar efficiency and reducing losses. So we hope that when cleaning tools are integrated in this system, it will be able to both find and clean dirt automatically, and it will enable solar maintenance to be a fully automated process that requires no human intervention. These are the key differences that supported our research. Thank you everyone for your attention. I hope this presentation gave you a clear picture of how an affordable ground robot powered by efficient data can make solar farms more efficient. I would now be happy to take your questions.